Very good. Thanks so very much indeed for the kind and generous invitation to this wonderful conference on the Munich quantum software project. It's a great pleasure to be here today in Munich. I should say that this is not a particularly rare pleasure. I noticed with an element of amusement that my rate of being in Munich is slightly above once per week, but that doesn't take away any of the fun of being here. So this is a relatively early talk on quantum error correction, specifically on a challenging decoding problem on so-called quantum low-density parity check codes and other perspectives of quantum error correction. That's the actual factual content of my talk. But there's also a meta message, and I might want to start with a meta message altogether, which is that we need functioning communication software. No, which is that quantum error correction is one of the fastest growing fields of quantum computing and presumably a great place for developing quantum software, which is why I feel very much at home here, and which is why you should see this entire talk as a kind of invitation to think in certain terms about things. So this is an early talk about quantum error correction. We hear a lot more tomorrow about this, but I thought it would be a good idea to say a little bit on where we go and what a brief history of quantum error correction could possibly be. How's the flickering? It's a bit... Can I compensate by just talking, or is that too bad? Well, never mind. Okay, so quantum error correction is not such a new idea. It builds on classical error correction, which in turn builds on redundancy, right? So if you want to kind of store a bit reliably, you can store this 0 into 000 and 1 into 111, and then if there's a small probability of this bit flipping, then if you have enough of them, the likelihood of you recovering the original bit is very high. The same idea doesn't work quite in the quantum world because quantum information cannot be copied by virtue of the no-cloning theorem. But what is possible, and that's a genius insight from Asher Paris from the mid-80s, is that you can do this on the level of the basis vectors of the Hilbert space and encode 0 into 000 and 1 into 111. And then you can take precious superpositions, precious quantum information, and if you then have a bit flip error, either no bit flip error or 1 on the first, the second, or the third qubit, you can look at all these 4 different situations and find that they're all orthogonal, mutually orthogonal. You can do a smart measurements, you can discriminate them and find out what has happened without learning actually anything about the logical information encoded, which would be a bad thing because then you would necessarily disturb the quantum information at the end of the day. That's a beautiful insight. Equally well, you can also speak about syndrome extractions, meaning you can make a measurement of certain Pauli operators, meaning you learn something of what has happened, but you learn utterly and absolutely nothing about the precious quantum information encoded. It's beautiful. It's from mid-80s. Who was born in the mid-80s? Never mind. But it's not quite a quantum error correcting code quite yet. It took another decade and the genius offshore to come up with the first quantum error correcting code, which takes like the quantum information, it does a Paris coding, and then Hadamard's along the way to go do another Paris encoding, going from the Z to the X basis, and indeed using 1 logical qubit to encode into 9 physical ones, you can come up with a proper quantum error correction code that protects a single qubit against arbitrary errors, Z errors, X errors, by that virtue also Y errors, but you can also bomb out an entire qubit, an arbitrary error on a qubit. So these are the code words. It's 9 qubits with a single quantum qubit coming in. So that would be, in this NKD nomenclature, would be a single logical qubit K encoded in a usually painfully large number N, I wish, of physical qubits with a certain distance, which is a kind of a quality measure of the code. That's the minimum weight of a Pauli operator to map one code word into the other. That's kind of how well the code will perform against certain errors. So the upshot is you take your quantum information with k qubits, you encode them into a usually much larger set of n physical qubits in a way so that if errors are occurring, then that will do something to the system, but this will map this guy into different subspaces that are basically left intact, and then you can make a measurement and learn which of these blobs you have, not learning anything about the logical information. You understand what's going on. That's a syndrome extraction. Once you know it, you can shift it back to the correction and come back to the original setting at hand. This is really getting a bit funny. I could just also improvise freely. Let's make it a bit of a, it is what it is, okay? There's very little I can do about this now. Good. So this is a beautiful idea. Again, you shall not learn anything of the logic information because that would necessarily and fundamentally disturb the information that you have. This was a first code, but there was another first code. Actually, a colleague working on trapped ion quantum computing in Oxford was a genius researcher, was a bit painfully underfunded at the time, but it seemed a good use of time to come up jointly with the theory of quantum error correction at the time. So he also formulated the basics of quantum error correction, in particular the 713 code, which is also encoding a single quantum bit, but even in a slightly more economical way, namely into 7 physical qubits, but with the same distance quantum error correcting code. These are the kind of the first codes that became available in the literature. They are actually both, and for that matter, most of these codes are so-called qubit Pauli stabilizer codes. There's also non-qubit stabilizer codes and non-qubit non-stabilizer codes, but most of the codes available today are qubit Pauli stabilizer codes, which basically means that there's kind of stabilizers that are collections of Paulis from the Pauli group, and you put them together, and the code space has the property of being in the eigenspace of eigenvalue 1 of all these stabilizers that again form a group, the stabilizer group, generated by certain independent generators. Much of that was formulated by this gentleman here that you can sometimes see and sometimes not. Dan Gottesman, who put much of this already in his PhD thesis, written at a time when I was not even academically born. That was before my time. Okay, so this is the setting, but you can also formulate criteria of how well this functions and what a stabilizer code can correct for concerning Pauli errors. There's these beautiful nil-la-flamme conditions that define normalizers, and they also give conditions whether and when a stabilizer code can correct for a certain Pauli error in quantifiable and computable criteria that you can evaluate in this fashion. So this was nice, it's beautiful, it gives the setting and sets the stage, but at the time there was an element of unease of relating this to actual physical, like planar hardware of superconductors or so. And this was changed when people thought about the toric code and the brother, sister of surface codes, which is by far the most common topological code that you can have. And the cute thing about this is defined in a 2-dimensional lattice with qubits sitting on the edges, but this is a bit of a matter of taste. Put them wherever you want, but it's a 2-dimensional lattice with a geometrically local connectivity pattern, so systems talk to their neighbors, which is a very beautiful thing when you want to think about physical implementations of a sort. So the stabilizers here, again, they're defined on spins, nicely on vertices and plaquette operators, which are dudes that involve 4 qubits at the time. So the stabilizer codes means that all the state vectors in the code space are in the eigenvalue 1 eigenspace of all these operators, but they are all geometrically local vertex and plaquette operators sitting in this two-dimensional setting, which is a very beautiful way to think about quantum error correction. Indeed, the logical dimension of the code space does depend on the topology of the manifold, meaning it matters how many ways you can go around, so it's 4-dimensional on the torus, so that k is 2. What is more, you have a knob of the distance, meaning if you have an L by L lattice, the distance would be like L, which means if you don't like the distance that you have, you make a larger patch and you've accommodated the distance that you want to see. This, maybe that goes a bit too far. I still say it that you can see this also as a ground state of a local Hamiltonian. In fact, as a topological Hamiltonian, there's an interesting connection of the whole world of quantum error correction to the physics. That's not a very physicsy audience. Who studied physics? Oh, okay. Never mind. And so in condensed matter terms, this would be a Z2 topological ordered setting. There's a close connection to so-called quantum doubles or even Levin-Wen models for non-chiral topological order. This is basically the same thing. There's almost a dictionary between the quantum error correction world and the condensed matter topological phase of matter world, with a cute way of going from one way to the other. Now, tori are cute mathematically. They're not so easy in labs. Don't talk to an experimentalist about tori. They get very nervous. The boundary conditions are a bit funny, but the key insight was by these gentlemen here who understood that you can make this planar on a 2D setting by the invention of the so-called surface code. And this is utterly beautiful. It's like a topological code in 2D with geometrically local interactions. It's 2D. It basically lays out the connectivity structure of superconducting devices, almost put in by hand. And this paper is like really great or evil, depending on how you put it. The worst thing that happens are the good results of the others. So this not only presents the surface code, which would have been a great paper, but it also it suggests like the mapping to StatMag models for bounding thresholds. It invents decoders. It makes the connection to topological order. Everything is in the paper. It's crazy, and everything else seemed a bit incremental afterwards, after this seminal paper. Maybe you could disagree, but I find this a pretty amazing paper. This was like setting the stage in 2002, and then other people also thought a bit in these terms. Then what Dan Gottesman calls sometimes the Middle Ages started, in the sense that people did good work, of course, things moved on, but quantum error correction seemed almost finished as a field. It's not like the hot stuff you can work on. People did interesting things, but it moved away a little bit from the mainstream hot stuff you could think of. But just like as in the real Middle Ages, which are often underappreciated, wonderful things happened. For example, quantum low density parity check LDPC codes were discussed, where every qubit interacts with a finite number of other qubits, so that the binary linear code, as we will see later, has a sparse parity check matrix sitting there. There were also like a couple of amazing challenges put forth, and the most prominent of those is to see whether good codes exist, so whether a coding rate would be constant, and where the distance would grow linearly in n, in the system size. It was like one of the holy grail questions, whether that was possible. People thought about fiber bundle codes and funny product codes and random encodings to ultimately see to the affirmative that such good codes exist, which is a great thing and very motivating. Now we live in the era of Renaissance, as we all know. There's new ideas coming in. That's also what this conference is about. And the field is much driven by new experiments on quantum error correction, and presumably the most cited papers along these lines, one of them was just cited a minute ago, is with cold Rydberg atoms of like 280 reconfigurable atom arrays, where there was like atoms sitting in some RAM, and they're put into a processing region and then put back where they made experiments with 48 logical qubits encoded into 280 cold atoms, which is a wonderful way of doing it. I was blown away. That was published just before Christmas, was the Christmas present to the community. I wouldn't have thought this was possible. We discussed this over lunch. It's quite slow. There's some buts, but it's a beautiful setting and quite forward-looking. Then, if you have a surface code patch, you can make measurements. They did this with a Willow chip. You get a syndrome. There's a classical site processor. You can process this, run a decoder, and find a fix for what has happened. And they did it, but not once or twice, but a million rounds with real-time decoding and feed-forward. This is quite amazing. These are 2 experiments that came out. Still, the overheads are insurmountably huge, and there's important software problems, which is what I will dedicate the remaining time I have to in what follows. So, decoding quantum error correcting codes. So decoding is a problem that's not quantum. Again, that happens also in classical error correction. Think of a binary linear code. So again, you encode 0 into 0, 0, 0, and 1 into 1, 1, 1 or so. You want to decode this. What would you do? A nice element to have here is the so-called parity check matrix. It's a matrix, the columns of which correspond to the bits in the setting. There would be 3 bits here, 3 columns. It's a generator matrix of the dual code, and the code words 0, 0, 0, 1, 1, 1 have the properties to be in its null spaces, meaning if you apply them, then up to mod 2 we will get a 0 matrix, so that if you have an error that has occurred, 0, 0, 1, you will see this by this not being mapped into 0, so errors are detected by syndromes by virtue of the parity check matrix. A nice way of representing that is by the so-called Tanner graph. It's a nice graphical representation. Graphical representation is always nice. I see Alex here in the front row who is like famous for graphical representations. I mean, I like to cite Feynman, who spoke about things that can be mathematically equivalent and psychologically inequivalent. This is mathematically completely equivalent, but it's psychologically inequivalent. It provides another representation. The bits are blobs here, so there's 3 bits for the 3 columns, and there's checks that reflects the constraint of the parity check matrix. So if you put in a 001, so that something is wrong, it has been flipped, this check would fire up, and you would see it in the Tanner graph here. That's very educational. Also, it nicely reflects the connectivity pattern of the device that you would have at the end of the day. So the syndrome equation is given an error E and the parity check matrix H, there's S as the syndrome, and the decoding problem is kind of to go the other way around. You don't see what errors occurred, you wish, but you see given S, given in syndrome that you've actually observed, what is the most likely error that could have happened that corresponds to this observed syndrome that you see at the end of the day. And decoding means solving that problem, and the clearly optimal decoder is a lookup table that just has a table with all the good outcomes and good solutions of the problem. That's wonderful, it's optimal, but it doesn't really scale so well. It scales exponentially with the system size. So people usually refer to inference algorithms like minimum wide perfect matching, belief propagation, and other settings of this type. Good. So how do you do it? Well, there's quantum CSS codes that are also very important. Again, most codes are CSS codes, Calderbank, Shor, Steen codes, which are basically like pairs of classical codes. They're defined by 2 classical binary codes, one for the X world, detecting phase flip errors or Z errors, or one for the Z world that detects bit flip errors or X errors. There's 2 parity check matrices, and a good example would be the Steen code, like the 713 code. RKD equals 3 color code. That's more like Tori code nomenclature for the same thing. So you have 2 parity check matrices, the X1, HX, and the Z1, HZ, and they're both the same, and you have like 7 columns, which are the 7 qubits of the code, and this is how these matrices look like. Then you think, oh yeah, cool, I have 2 problems, I just decode the X and the Z parts alone. I wish. It's not so easy. Things don't work that way so well. The problem is that errors tend to propagate, and they can appear on all places of the setting. If you see not, the error would propagate in both directions, and if you append auxiliary systems, and there would be errors occurring all the way, they could propagate back into the setting on all levels. So errors propagate in circuit implementations for circuit level noise, like depolarizing noise, and they would go all over the place. So what you would need is to have like error propagation rules that tell you what happens and where errors go and how they can connect to different parts of the setting. So this is a bit of an art form in its own right, but one way of looking at it is to go from the parity check matrix and define a new one, but on a higher level. It's called a detector error model, but that's yet, in a way, another parity check matrix that accounts for the circuit level faults to accommodate them. So that's like a detector matrix that connects the circuit faults that happen on all places in the circuit to linear combinations of stabilizer measurements. So it's, in a way, another matrix, a detector matrix with a binary linear code that can be decoded in the ordinary sense with a decoding problem that takes the same formal structure with a code syndrome, a binary check matrix, and an error, but then for a larger matrix that kind of encapsulates this propagation of errors in circuit level noise in the actual circuit implementation. We didn't invent this. I'm not even sure who did this, like Craig Gidney maybe, or Campbell also mentioned this earlier. This is a paper where we mathematized some of this, and it's a bit of a preview, and a kind of meditation on the topic of detector error models, which are very useful in this context to keep track of errors. So just to give you an insight, it's very useful, it's very practical, but the thing is that things become quite quickly quite nasty. So this is a picture that shows the parity check matrix for a D=3 color code, aka the 713 code that I mentioned earlier. If you look at the circuit level detector matrix with a syndrome extraction circuit and 3 measurement rounds, the graph looks a bit like that. What's the meta message here? It's messy and it's large. So the upshot is it matters how quick you do things, because things are fast, you better think about efficiency of doing things in reality. So decoding comes with a wish list, with desiderata. Decoding has to be, first, fast for that reason. Why? Because there's vast amounts of data being produced in measurements in the quantum computer. They are being sent to a classical supercomputer next door that runs the decoding algorithm and makes smart choices, feeding it back to the quantum device and doing the recovery. And this beta is faster than the noises actually accumulating in real time in the hardware. So you fight against the real hardware working against you. So the quantum computer, and there's the classical supercomputer, and there's the nuclear power plant as the third part of the triangle, not in Germany though, but in many other places. So this has to be fast, but there's more to this. It also has to be versatile, meaning quantum memory experiments are not everything. That's one thing, but you have to also do logical operations. You want to implement actual circuits in a device, and then the decoding graph is constantly evolving in time, so you better use the previous settings in your scheme to make choices in the next steps. And the quality of the decoding determines the quality of the quantum error correction. So the balance must be struck. Accuracy is a good thing, but you also want to be fast enough. There's a bit of a compromise, so you better strike the balance between accuracy and the performance of this, because that determines the performance of the entire quantum error correcting scheme. That's kind of the wish list of what we want. Decoding with belief propagation and ordered statistics decoding. So in the classical world, there is a nice scheme called belief propagation that covers most of the decoding problems. So here's again the decoding equation with syndrome equals h times e. And for an error in the parity check matrix, this is to be solved. The decoding goal is to find the minimum weight estimate that satisfies for a given syndrome that you have measured the argmax over E, And this can be turned, this is complicated, it's innocent looking, but E is like all the outcomes of the errors that are happening in the entire setting. Now, if you have like IID noise and the errors are like IID distributed, the whole thing becomes a very multivariate distribution, but you can write the distribution for one dude as a sum, as a marginalization problem over each bit, which is formally true, but it has exponentially many terms that you have at the end of the day. And the core insight of belief propagation is to use like the Tanner graph and make use of pre-computed sums as messages in an iterative message passing algorithm to break down this exponentially large sum into handleable smaller sums that can be pre-computed and iteratively approximately computed through message passing. So that's approximate on graphs with cycles, but it's often good enough. When you came in, of course, the first question at every conference is, what is the Wi-Fi password? If you use Wi-Fi, you're using 5G, and you're basically using belief propagation as decoding, which is a very common way of doing it. And that works very well in practice for classical codes. It's fast, it's versatile, it's accurate, and solves your problems. This has also been, of course, used for quantum error correction. Now, it has no threshold for the quantum toric code, unfortunately. So this is because it does not work for all error configurations, and there's many degenerate configurations, so the whole thing gets stuck along the way. Or another way of saying it is the Tanner graph contains many short loops, which is not so good, and then you get the belief propagation will get stuck in so-called trapping sets, and you will not get out. And if you make a plot, you see that there's actually no threshold. The blue curve is it's not the largest, but it's the smallest system which performs best, and making the system larger makes things worse and not better. Yuck. You don't want that. So it doesn't quite work in the way it should. But this can be fixed with so-called ordered statistics decoding. That is like a post-processing scheme on top of belief propagation, where you have syndrome coming in, you run belief propagation, and then you get an output. If you satisfy the decoding conditions, you say, yes, great, output it. And otherwise, you try to fix it and force a solution through matrix inversion. Now, this parity check matrix is not invertible, it's not even square, but you can think of a full rank submatrix, but then you have to make a choice, which one do you pick? And the genius insight comes in through using soft information from belief propagation to fix that submatrix and then invert it and force the solution to make it happen. That was originally classically developed as a method for reducing the error flow for classical LDPC codes, but has been applied to the quantum setting in this beautiful paper by Pantalev and Kalachev, and now is bread and butter in this world to make things happen, and it's a one-size-fits-all decoder for quantum LDPC codes. It has a threshold for the toric code, it works well, it's reliable. Belief propagation plus ordered statistics decoding is a great way forward. So it's fast, it's versatile, it's accurate. Now, this ordered statistics decoding requires Gaussian elimination. That's n to the power of 3, but that's too slow at the end of the day. Can we do fast decoding? And this brings me to the fourth and the last part of the main part. On decoding QLDPC codes with localized statistics decoding, that's supposed to bring all this together as a coda of this talk, if you want. You want to be fast, you want to be accurate, you want to be versatile, sort of look into the thing in the center. We want everything there at the same time. How can we do this? And here's the intuition. So the point is that we want to do like some sparsely aware matrix inversion, because QLDPC codes are sparse. There's like constant many neighbors, which means that you have errors that there will be somewhere below threshold. Errors will span independent regions of this decoding graph, and they will not talk much to each other. So the matrix inversion problem as such will also factorize. It will be kind of independent. And the intuition is great. Taking that seriously, you should be able to think of independent decoding regions, decode them in parallel, and that could also be accommodated on the level of the algorithm. Think of patches. And this was the core idea underlying this approach taken. So some region here, one there, and then you want to see what happens in these regions. Now, the first step here is to run belief propagation. So you run belief propagation, you get soft information from the belief propagation that gives you an intuition on where you are in the setting and where the errors have occurred in the setting. And then you start growing clusters. You do that in parallel, you grow them from each activated syndrome node that you have, and you grow them one by one, bit by bit, and you grow them along the way. You grow from each activated bit, expand one bit at a time. Sometimes the clusters can collide, and when they collide, you would merge them to a larger cluster that you have here. So this makes larger and larger clusters, and the cluster growth is halted where the cluster supports a solution to the local decoding problem so that you can locally on the patch solve the decoding problem that you have. And so this means a cluster is valid if it can be inverted on that part. So if you can solve the local decoding problem and you can invert that matrix that got a full rank, or in other words, the cluster is valid if this syndrome that you see is in the image of the parity check matrix, and then you can locally invert this and do the decoding on the local patch. And so how do we, that's a halting condition, how do we efficiently verify that halting condition? And that's, this is like much of the substance. Of course, you can run Gaussian elimination in each step, but that requires of the order of the cluster size to the power of 4 many steps on the largest cluster size, which is a limitation. And here we've introduced a new algorithm, what we call on-the-fly elimination, that dynamically eliminate cluster size as they grow, in worst case, with a better scaling in the cluster size. And that's actually much of the meat of this paper, where we kind of technically solve linear systems over finite fields with a PLO decomposition, so in terms of permutations, lower triangular matrices and upper triangular matrices to make them numerically stable, which works in order n. But it has many cute features, namely that you can build up stuff step by step. You can use what you've done before, and then you grow the cluster, you append another column. You can use what you had before, and you can just append this on the right-hand side and massage the matrices to keep the form that you have. You have two clusters colliding, but in subleading performance, you collide them, and you get another parity check matrix out. And this, put together with the 3 steps, gives a fast, a versatile, accurate decoder where you do the patches separately, largely in parallel. It's fast, it's versatile, and it's accurate. That works well. On paper, of course, the proof is in the pudding, or you have to show how it works in practice. We've tested this on common candidates of the rotated surface code with circuit level noise, on the hypergraph products, which are common QLDPC codes, on the famous IBM bicycle bivariate codes with very good thresholds, and also with very nice performance concerning the parallel implementation. So this performs very well, and it's a nice showcase of how quantum insights, on the one hand, like physics insights and how this is realized, and quantum software come together to make a decoder that scales well and has all of the desired features. This is a glossy and short paper, came out in Nature Communications not long ago. It's like 5 pages or so, but it has very long and winding appendix with lots of details. For example, we have a lot of connoisseur material for the mathematically minded people on, say, site percolation, on how many clusters you're expecting, how large they are. Not everything is fully rigorous there. Some parts are, but this is an invitation to think hard about this, because I think you can really rigorously almost push this to a completion. My clock says 34, so that brings me to the outlook phase of the talk. So in this talk, we looked at the important problem of decoding quantum error correcting code. There's no detail, there's no quantum error correction without decoding. It takes syndrome information, you make smart choices, and you see what you do to fix it. And for the known schemes, they were not fast, accurate, and reliable. At the same time, we kind of found a versatile way of getting all the desiderata into one and have a scalable thing. Quantum error correction is a great playground for quantum software. We found a fast, accurate, and versatile decoder for QLDPC codes that have nice features, but they really work well in practice when you run them with quantum software on a machine. But what else is there? I said this is an invitation, so what can we think about? And I'll throw a couple of thoughts into the room. First of all, there's stuff happening in the system. Knowing a noise is very important. Say, we discussed this over lunch. Say, if you don't do quantum error correction, if you deep quantum circuit, you have no deep quantum circuit. What you have is a logarithmically deep quantum circuit. On average, in a very strong sense, log depth is all you have. If you have a deeper circuit, chop off the first part, put in the birthday of your grandmother or the identity, log n will matter. That's not the end of the world. Log n is log n. The numbers matter, but without quantum error correction, log n is all you have. You can do quantum error mitigation. That's also what we discussed. You can push the quantum volume, but there's an obstruction against quantum error mitigation at log depth. There's a mathematician's joke that log is upper bounded by 4. It's a good joke when you think about this. It just means it should be done, it must be done, but it's not scalable in the most drastic of all senses. But putting it to our theme, knowing your errors is very important because whether it's non-unital or not matters, and you can largely tailor codes to the noise model that you have. And that gives you much better thresholds. It's also a software problem to tailor that to the setting at hand. Then think of the other desiderata of your device, like locality. The days are over when you just do some abstract codes. You better think of how the things function and how the locality is in your device. So on the highest level, there's here Alex Kissinger type ZX calculus rewrites that kind of sequentially bring you through, or you can formalize the setting as a global optimization problem and run quantum software to find hardware-tailored circuits. Presumably one should merge these two different approaches, which is highly fruitful. This is an invitation to think about quantum software to accommodate hardware designs. Continuous quantum error correction is largely underrated. We thought, can you do good codes in the GKP world? You can, but this is only starting. There's two communities that are not even talking to each other so much. It's kind of funny, it's almost separate, but we found that there's good codes and there's also interesting connections to mathematical lattices that I'm happy to explain that in case you're interested. Think more about continuous is my life advice. And finally, last slide, measurements are underestimated. Like for cold atoms, we know how difficult that is. Complicated measurements are not something you want to do, and you have to think in terms of ways of how to bring that down. Fortunately, we have tools. Say, Floquet codes. You've complicated 8-qubit measurements that make your head explode, but you make settings like ABC, ABC, ABC. You make schedules, and the little snippets are so that the overall instantaneous stabilizer group is right. You get the same code space, but you bring it down to little snippets, and we, for example, thought about Floquet codes with 2-qubit measurements in the color code phase with attractive thresholds. Why am I saying this? Because it gives yet interesting software problems to bring down the burden of measurement. Which brings me to the end of the talk, which is the meta message. The fun with quantum software and quantum error correction is only starting. We are kind of bringing the physics of the game into the game, like the locality, the noise, this comes together. But this is like more of an invitation because that brings in lots of fun software problems to accommodate for these desiderata. And on this note, I thank you very much for your attention.
Thank you, Jens.